All right, let's take a look at these guys. Remember what I said about reducing radicals? What's the easiest thing to make sure you do this right is? Remember, we wrote some stuff down on the left-hand side over here? Yeah, 2, 3, 4, 5, 6, 7, 8, 9, 10 even. And then just write down all the squares. And you can do this right on the test if you want to remember it. 4, 9, 16, 25, 36, 49, 64, 81, and 100. OK? And now you can start looking down this list and seeing if any of these go into 80. And in fact, a couple of them do. What goes into 80 from this list?
16.
16 does?
4.
4 does. We can do it either way. OK? Let's do the 16 one first. OK? So you divide 80 by 16, and that gives you what? 5, right? So and do that on your calculator if you don't. If you want to. That's cool. 16 times 5, right? And then I always cross out the 16, because I know I'm going to have to take the square root of that. Then you take the square root of that, and this ends up 4 times the square root of 5, and you're done. OK? All right. We also said that 4 goes into 80. Fine. If that's the first one you come to and you go, that works, try it. You go 4 goes into 80. How many times? 4 goes into 80 20 times, right? So this is going to be equal to the square root of 4 times 20, which becomes, well, you cross out the 4 and you take the square root. 2 times the square root of 20. You're not quite done yet, because is there anything else that goes into here? 4 again, right? So you have to do the same thing. You have to do it again if you end up with something that still can be reduced. So 2 square root of 20 is going to be 2 times the square root of 4 times 5, because 4 times 5 is 20. Same thing, cross out the 4, and know that you're going to have to multiply the square root of that times the 2. Well, the square root of 4 is 2 again. Times 2 is 4, and you end up with 4 times the square root of 5, which is hopefully the same answer. Because now 5 is definitely as reduced as we can go. So it is the same answer. OK, so you can do it either way. It doesn't really matter. Just remember that you got to always look and see if this is reduced before you can say I'm done. OK, questions on that? All right. Now let's look at the other one. Rationalize the denominator. Now remember, I said this is one of those ones where it's silly to do these days because you can actually have a calculator to just do this on the calculator. But we still need to at least know how to do it. What's the trick to doing this? Or not the formula, or the algorithm, or whatever you want to call it? Multiply, well, right. There you go. Multiply top and bottom by the denominator in this case. Square root of 23 over square root of 23. OK? And by the way, if this was like 2 square root of 23, you'd still just multiply by square root of 23, which is cool. But we can do another one like that if you want. And then you end up with, on the top, 5 times the square root of 23 divided by, what's square root of anything times the square root of anything? It's itself, right? So this becomes just 23. And we're actually done with this one, right? If you could divide that into that, you could reduce this like fraction. Or if square root of 23 happened to be reducible, you could reduce that some more. But really, on the test, I would let you get away with this. On the homework, they're not going to let you get away with that. But on the test, no worries. OK? All right. We good for the warm-up? All right. All right. So tonight, we have to do a few different sections. We're actually going to jump around a little bit. We're going to start out with section 5.5. Then we're going to do section 5.6. Then we're going to actually jump back and do section 1.3. Remember how I said that a lot of the problems on the final exam in here are going to be word problems? Well, the word problems they take problem-solving strategy. And as it turns out, section 1.3 in your book talks about problem solving. So we're going to go through some kind of generic ways to solve problems, which is, hopefully will be helpful when you get to test questions and so forth. So we'll do some examples of that. All right, anyway, let's start with section 5.5, which is called real numbers and their properties. OK, real numbers and their properties. I always thought teachers should have a class in penmanship, because I've got terrible penmanship, and they should teach you that in teacher school. Yeah. They do teach you one thing in teacher school. Did you know that you're supposed to erase the board up and down and not side to side?
You go.
Yeah, if you do it, if you do it side to side, your butt jiggles.
Yep.
So always erase up and down. All right, anyway, real numbers and their properties. OK.
You were wiggling last night.
I wasn't. Well, all right. Try to remember. OK, so real numbers and their properties. All right, so remember last night we started with the types of numbers, right? We've got natural numbers, which start with what? 1, just like you naturally count. OK, and then you have whole numbers, which start with 0. It's that extra number that they finally figured out after thousands of years. And then after whole numbers, you've got all the negatives, which make up the what? Integers. Good. And then you've got fractions, which we also call rational numbers. Right? Rational numbers are numbers that can be expressed in the form some number over some integer over some other integer. What's the one key thing about b that it can't be? It can't be equal to 0. If it's equal to 0, it doesn't fit in these numbers at all. In fact, it's an undefined quantity. OK, rational numbers. We've got two types of rational numbers. Remember, there are the ones that stop, the ones that don't repeat forever, and then there's the ones that do repeat forever. They're the terminating ones stop after a certain number of digits. The non-terminating ones have some repeating section that you can say those numbers repeat over and over and over again. 0.898989. That's the repeating part. That is therefore a rational number. Okay, it's a rational number, and we learned a way to get from this back into this form. You want to go over an example of this one more time? Yeah. Why not? This one, 0.898989 repeating. What was the first thing we did for this? No, before that, we just wrote it down. X equals that number. Well, there was something involved. You were close. How many digits repeat? 2. 10 raised to the 2 power is 1 with 2 zeros after it. That's the number that you're going to use to do this tricky way of figuring it out. So we're going to end up with 100 times x equals 100 times this guy, which just moves the decimal place over 2 and makes this 89.898989. OK, or the little bar like we're used to doing. Then what do? Subtract these. And this is like algebra, like a little bit of just about algebra, right? 100x's minus 1x gives you 99 x's, right? 89.89898989 minus 8.89898989 gives you what? 89. Now this is like rule number 1 for algebra. If you've got two numbers multiplied by each other, you divide to get rid of one of them by that number. And you have to do the same thing to the other side. And therefore, these cancel out. And you're left with x equals 89 divided by 99. And if someone does that in the calculator, hopefully you'll get this number. Right? OK. That's about as hard as those ones will get. OK? All right. Still a rational number, though. Even though it repeats forever, it's still a rational number. OK. And then finally, after the rational numbers, we had irrational numbers. What's the most famous irrational number? Pi is an irrational number. Why? Because it goes on forever. 3.14159265359. I think it's 9. Anyway, and it just keeps on going, but there's no discernible pattern. One of the interesting things about this number, it's still unknown whether there's the same number of 1s and 2s and 3s and 4s and 5s as all the other numbers. Still unknown. That would make this what we call a normal number, just because of the way it's distributed. But that's still an unknown problem. So if you ever want to be a mathematician, you can maybe work on that. I don't know, big number theory sort of thing. So anyway, all of those types of numbers are the subset of the real, are a subset of the real numbers. OK? So whole natural numbers, whole numbers, integers, and rational numbers are all, and irrational numbers are all considered real numbers. The non-real numbers are like the square root of -1, or the imaginary numbers, right? We're not even going to worry about those in this class. Okay? They're all the subset of the real numbers. Okay, and they all fall somewhere on that number line that we talked about. Okay, so any of these rational numbers, you can point to a place in the number line and say that's where that number is. And if you kept zooming in more, you could get more and more defined about exactly where it is. Okay, all right. So let's see if we can place some of these numbers into various groups. Okay. So let's say you had a set, and by the way, that's a terrible curly bracket. There we go. I would have learned that in the penmanship class if I'd taken it. When we write a set of numbers, we'll normally do it in these curly braces like this. Okay? 18, negative 5, 7/12 pi, 3 times the square root of 2, and negative 4/15. There we go. OK, those numbers, which ones are whole numbers? 18, that's a whole number. Any other whole numbers? Nope, because none of them are between 1 and infinity. OK? Or 0 and infinity, I should say. OK, integers. Which one's an integer? That one's an integer. How about, is that also an integer? OK, also an integer. Anything else? Nope. Rational numbers. Which ones are rational? 7/12 is rational. Is 18 rational? Can we write it 18 divided by 1? Then it's rational. Right? If you can turn it into a fraction like that, it's rational. OK? You can't. Some of these ones, well, pi, this doesn't count. You can't say 3.1 divided by 1 and say it's rational, because the top part's still irrational. OK? That one doesn't work that way. OK, so let's see. Rational. This is rational then. Negative 5? Yep, also rational. Any of the others? Negative 4/15 is rational. Does it fit in the form a over b? Yes. Sure. OK? And is 15 not equal to 0? Yes. OK. All right, let's see. Irrational. Pi, of course, is irrational. I already used I. IRR. Pi is irrational. How about any of the others? 3 times the square root of 2. Remember, square root of 2 is irrational. You can't get any, you can't reduce it anymore. And when you type in your calculator, it just goes on forever like that. OK? I believe any rational, let me think about this. Yeah, I believe any square root that you can't take you can't reduce it more is irrational. Don't quote me on that, but I'm pretty sure that's the case. Anyway, this one happens to be irrational. OK? All right. So on the test, the first quiz, which happens to be next Sunday, and today I'll give you a review packet for that, you're going to have to place numbers like this. Pretty simple stuff, really. Just remember remember the kinds of things that we're doing here. Questions on that? OK. All right. Oh, now you're going to look at me when I'm erasing. Uh-oh. OK. Now let's talk about some properties of the real numbers. Properties of real numbers. Now, you may remember some of these terms from like when you took them, however many years ago they were. They're not that hard. Like I remember getting all confused about these and having to sit here and try to remember what each of these properties were. But it's really not that hard if you think about it. If you pay attention and then like process what's going on when you look at these these types of properties. OK? All right. By the way, this is on page 277 in your book. There's all these properties. You do not need to go in the book. And for those of you who weren't here when somebody asked earlier or yesterday, you don't have to bring your book to class. I'm never going to say open your book and look at page whatever. But I might write down things like this so you can go home and look them up. OK? All right. Properties of real numbers. And by the way, if you haven't figured it out, your My Math Lab has your book in it. And you can read the whole book right there. It's not the easiest way to read it, but it's there if you want. OK, properties of real numbers. OK, so let's look at some properties which are which we call additive properties. OK, additive, A-D-D-I-T-I-V-E. Additive properties are about when you're adding numbers together. Pretty simple, right? When you add a real number plus a real number, a plus b, can you end up with a number that's not real? We won't go and prove that, but if you can think of any example, I bet you can't think of any examples where that's not true. You can always start with two real numbers, add them together, and you'll end up with a real number. Okay? The property that a plus b is real, that is called the closure property. Okay? I'll put the property over here, and like the, I don't know, this is the definition over here if you want. Okay? Closure property is just that a plus b is real. So if I said, what's the closure property for addition, you'd say a plus b is real. Fair enough. Now, let's say you have a plus b. Is it true that that equals b plus a? 5 plus 2 is equal to 2 plus 5, right? That's true. Now, this is called the commutative. C-O-M-M, two M's, C-O-M-M-U-T, commutative. The commutative property. Here's how I remember this one. Commutative kind of sounds like commuting, like you're commuting to work. Look at A. A commuted to the other side of B. That's just the way I remember it. You remember however you want. But I kind of remember it like that. Numbers that add like this are commutative. Okay? It doesn't have to be just A and B. It can be like 5 plus 2 plus 7 equals 7 plus 5 plus 2. See how the 5 moved to the middle and the 7 moved to the end and the 2 moved around? That's just the commutative property. It's just one of those properties. We like these properties, by the way, because it makes it so that we can solve problems that involve unknown letters. Algebra, basically. Okay? So this is this commutative property. All right, there was something else I was going to say about that. Is subtraction commutative? 5 minus 7 equals 7 minus 5. It is not, right? You could say 5 plus negative 7 equals negative 7 plus 5. Does that work? Yeah. Sure, because that's now you're adding those two distinct numbers. But subtraction is not commutative. These are why this is the additive properties. Okay. All right, the next one. OK, we can also say something like this. A plus B, okay, plus C equals A plus B plus C in parentheses. Now remember our orders of operation yesterday. Always do the stuff in parentheses first, and then do the whatever comes after that, right? Is this true? You can add two numbers, then you can add the third, or you can add the second and third number and then add the first two, and then you get the same number? You can, okay? This is called the associative property. Okay? The way I remember this one is that it's like when two people associate with each other, they're like together, right? So here's these two guys, they're associating with each other, and now these guys are associating with each other. Did anybody move places? No, if they'd moved places, that would have been the commutative rule. Okay? By the way, we're not going to mix and match. Like I could have done B plus A plus C, et cetera, and then that would have been like both rules. But we're just doing one rule at a time for this kind of stuff. Okay? It's called the associative rule. A and B are associating here. Other over here, B and C are associating. Okay? We kind of innately know this, but 0 plus any number just gives you that number again. 0 plus A, being any number, gives you A. Okay? That is called the identity. The identity. 0 plus A equals A. Okay? Which also equals A plus 0. But that would be the commutative part of it. Okay? Identity. Why is it the identity? Because you get back what you started with. 0 is the identity for addition. This is the identity property. 0 plus anything equals that thing. Okay? And then finally, we've got one more property. Let me show you what it is first. We've got one more property. A plus negative A equals 0. this looks somewhat similar, right? But this is just called the inverse property. Okay? What it means is there's some other value related to the first one that gives you the identity value when you do this addition in this case, right? So we've got the value a plus the negative a gives you 0. Fair enough? Okay, and that's called the inverse. All right. Closure, commutative property, associative property, identity property, and inverse property. Any questions on those? Okay. Here's what I'm going to do. I'm going to erase all the definitions, and we're going to do the multiplicative properties. Okay? Now we're going to do the multiplicative properties. Okay? And I'm going to erase all these guys like this. There we go. And you're going to have the same properties here, but we're going to have a different form of them. Okay? And actually, we're going to have one more property after this. Maybe one more? Yeah, I think just one more property after this. So all these properties also are true for multiplication, but we have to define them first. Okay? Remember how before the closure property was a plus b is a real number? How about a times b? Do you always get a real number? You do, right? Two real numbers always give you another real number. Two real numbers multiplied together give you a real number. Okay? Is there a closure property for division? Two real numbers divided by each other always give you a real number. Randy, can you give me an example?
Say divide 15 by
15 by what?
30.
30. That's not a real number? That equals 1/2. Is 1/2 a real number? It is. Not a good example. Good try, though.
Yeah.
OK, let's pull out. There might be one. What was the property of rational numbers that's really important to know?
0.
So our two real numbers, let's say 15 and 0, are they both real? Can you divide them both by each other and get a real number? In one case you can, but not in the other. 0 divided by 15 is indeed real, because that's 0. 15 divided by 0 is not defined. It's not 0. It's not infinity. It's just not defined. So that means division does not have this closure property, specifically for 0, in fact. Okay? All right. The commutative rule. Remember, commutative was like the a moved over somewhere. So a times b, does that equal b times a? Indeed, it does. Okay? I could also write this, by the way, just ab equals ba. Sometimes if we have single letter variables, which a lot of times we do, we just get rid of the parentheses, we get rid of the times symbol, we get rid of the little dot, we just write them right next to each other. Okay? But in this case, those are equal to each other, and that is the associative property. Okay? The associative property. Oops, sorry, I lied. The commutative. What did we? Oh, sorry, I'm looking at the wrong line. The commutative property. Yeah, there you go. OK, the associative property was the one where the two guys associated with each other, right? A times b times c, or a times b times c in parentheses. A true statement?
Yes.
You can work out some examples and see that it's probably a true statement, right? But it is in this case. It's the associative property. A and b are associated with each other. Now b and c are associating with each other. Okay? All right. The identity property. The identity property gives you back what you started with. What's the identity property for multiplication? 1, right? The 1 is the identity, right? So 1 times a equals a. You get it right back, or a times 1 equals a. You get your number right back again. The inverse property. OK, the inverse property is slightly different in the sense that there's one little caveat with the inverse property. OK? A times what will give you the identity? A times what will give you the identity? 5 times something gives you 1. I like that. 1/5. Right? So A times 1 over A will give you 1. There's one problem, though. What does this remind you of? Our little problem with division, with rational numbers. The 0, right? A cannot be equal to 0. So you have to say, if A is not equal to 0, then A times 1 over A gives you 1. Okay? A lot of people forget this. When we get to doing algebra, you're going to forget this stuff, and you're going to go, I don't know how to get rid of that variable. For instance, you're going to see something like 5 equals A times B. Solve for A. And you're going to say, well, that's not a very good example. Let me do it this way. 5 equals A divided by B. Solve for B. What you'd do is you'd say, look, we can now multiply both sides by B, because B times 1 over B, forget about the A for a sec, those B's cancel out. You're going to forget about that when we get there, so learn it now. Well, we'll go over it step by step when we get to that problem. But this is a big one for solving algebra problems. Okay? The inverse rule. Okay, so there we go. We got all of them. Any questions on the multiplicative properties? Okay, those are the multiplicative properties. There's one other property, okay, which actually is combining both multiplication and division. Can I erase these? Everybody's good? All right. There's one more property, and this is another really important one. It becomes really important later in the class, and you'll see why when we get there. But there's a property called the distributive property. Distributive property. And we say that it's over multiplication and addition. Okay, the distributive property of I guess it's really of multiplication over addition. I'll show you what I mean. And the over is not like a divided by over. Okay? If you have A times B plus C, some other variable, B plus C, what you can do is you can distribute the A through both of the variables over here. Okay? It's called the distributive because you're distributing A. What this means is you can say A times B plus A times C. Okay? So let's do an example. 7 times the square root of 2 plus 8. Okay, first question. Can you add the square root of 2 plus 8? There's no way to do that because you've got a radical in there, and you can't add a radical or a square root plus any other number unless it has the same square root on it. Okay? So no, you can't do anything with that. We can distribute the 7 through here, though. What's 7 times the square root of 2? 7 square root of 2. 7 square root of 2. Okay? And then you also distribute the 7 through to the 8. You multiply those two plus 56. Okay? Now you've distributed that through. Okay? We can go backwards on this as well. Okay? This is a little trickier, right? But in some cases we need to do this. Not always, but sometimes we need to do this. 7 goes into both of these, doesn't it? So we can kind of go backwards here. We can say, let's take a 7 out of both of them and put it out front. 7 times, well, this divided by 7, because we got rid of 7, it's just square root of 2, plus, and then 56 divided by the 7 gives you 8. So you kind of go backwards. You'll see that less often, but it's still an important kind of concept. Okay? All right. All right, let's do a couple examples of some of these other properties. Okay. All right. Let's see. 2 times 3 equals 3 times 2. What's the property? Commutative property of? multiplication. Very good, okay? Commuted. 2 moved to the other side. Okay? How about 1 times 3 equals 3? The identity of multiplication. Okay? 1/2 plus the square root of 17 plus 4 equals 1/2 plus the square root of 17 plus 4. Associative, right? These two associated with each other. Now these two are associated with each other. Good. And then, let's see. -3 times -1/3 equals 1. The inverse property, right? By the way, this is one of those times where the fact that a negative times a negative equals a positive makes some of the other math work. Because 2 negatives give you a positive. Well, -1/3 is the inverse of 3. And we know that inverses multiplied times each other give you a +1. So this is one of those examples where that's a good thing. OK? All right. Let's see. I think that's good for this section. All right. Any questions on that stuff? All right. All right, let's move on to, we'll do a little bit of the next section, and then we'll probably give you a break after that. All right. All right, so that was 5.5. Now we're going to go into 5.6. 5.6, okay, is about exponents and this thing called scientific notation. Okay? Exponents and scientific notation. 5.6. Exponents and scientific notation. I like this one because I'm a scientist by training, and we use exponents and scientific notation all the time, and it's actually kind of cool. And I'll show you why in a second. OK, exponents. Remember how multiplication was just repeated addition? A times b equals a times a times a times a, however many times, or a plus a plus a plus a, however many times b is, right? Well, exponents are just repeated multiplication. Exponents are repeated multiplication. Okay? 3 raised to the 4th power. It's an exponent. That's called the exponent of 3. 3 raised to the 4th power equals 3 times 3 times 3 times 3, which happens to be 81. Okay? The nice thing about exponents is that you can actually combine some exponents when you multiply them. Like if we had a number b raised to the 2 power times b raised to the 5 power, look what that means. B times b is this one, right? Times b times b times b times b times b, which is the other one. Well, what does that equal? B times b times b times b times b times b times b, b to the 7th. So guess what? A raised to the b power times a raised to the c power equals a raised to the b plus c. You just add the two if it's the same base. Okay? It does not work for things like 3 to the 4 times 2 to the 6. You can't do anything special with that. Okay? You can't do anything special with that. But you can if it was 2 to the 4th and 2 to the 6th. You would just say that's 2 to the 4 plus 6 is 10. Okay? One of the reasons we use exponents is because it makes it easy to talk about really big numbers and really small numbers. Okay, we'll get to the small number part in a minute. The big number part, let me give you an example. So let's say I was to ask you, say we were talking about the universe, right? Now, by the way, the universe has roughly, well, it has galaxies in it, right? Remember how we're part of the Milky Way galaxy, right? We have our solar system, then we have our galaxy. This is like science time. The Milky Way is our galaxy, right? Any guesses about how many galaxies there are in the universe?
Trillions.
Trillions? Probably not quite trillions, but probably about 100 billion, right? Which is what? Let's see, a billion. Anybody know what a billion is in scientific notation? How many zeros there are in a billion? 1, 2, let's start out with this. How many is that? 1,000. What's the next number that we normally talk about when we talk about bigger numbers? 1,000, then 10,000, okay, 10,000. Then we get to 100,000, then we get a million, and a million has 6 zeros after it, right? Well, the next big one is actually 3 more zeros. That's a billion, okay? If we have 100 billion stars, that's that big. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's 10 to the 11th galaxies, okay? So notice that's a big number. And notice how easy it is to write in scientific notation, 10 to the 11th, right? How many galaxies do you think there are? Sorry, there's this many galaxies. No, what did I say? How many galaxies? Yeah, how many galaxies? How many stars do you think are in each galaxy? About 100 billion again. About another 100 billion, 10 to the 11th, right? 10 to the 11th and times 10 to the 11th is what? 10 to the 22nd, because we add the two together, right? So we're getting kind of big numbers here, just writing a little 22. OK, here's the big question. You know how your body and everything that is made of matter has electrons and protons and neutrons, and there's trillions and trillions of electrons, protons, and neutrons in your finger, right? Trillions and trillions. How many total particles do you think there are in the entire universe? Don't try to do it in terms of like a regular old number. Try to do it in scientific notation. 10 to the what, do you think? What's your guess? 100? What other guesses are there? All the particles. Remember, there's trillions in your little finger, and there's and that means in this room there's like trillions and trillions and trillions. Any other guesses?
Way higher than that.
Way higher than that? 10 to the what? Nadia, what do you think? 10,000? That's pretty big. Okay. Turns out, and people will disagree on this to some extent. Turns out there's about 10 to the 85th particles in the entire universe.
That's it?
Okay, you say that's it, right? But remember, numbers get big. Like big numbers are easy to express in scientific notation, right? Turns out, so let's look at what we got. We started with 10 to the 22nd stars, right, in the universe. 10 to the 22nd stars in the universe. Now let's think about how much stuff fits into a star like the sun. Okay, you can hold about, let's see. Anybody remember what a mole is? A mole is 10 to the 23rd of something, right? It's how many? It's actually the number of what is it? The number of atoms of carbon in 12 grams of carbon. So you can hold that's like this much carbon, all right? Actually much smaller than that. But that's 10 to the 23rd. 10 to the 23rd. Okay. How much would be? Could you hold like in two hands maybe if you held them like this, 10 times that much?
Yeah.
10 to the 23rd times 10 to the 1 is what? 10 to the 24th. OK, so now you've got 10 grams of whatever. 10 times that is how many? 100, which might be like this big, right? Which would make this number go up to what? 10 to the 25th. OK, and now that's 100, which is like this big. OK, 10 times that is 1,000, which might be like this half of the room or something, right? How big's the number now? 26. OK, 10 times that is 10 halves of the room. Let's say it was just like, let's say the thing was a little bigger, and we said we got a whole double-wide clue worth of that stuff. That's now what? 10 to the 27th. 10 times that is like 10 clues. That's 10 to the 28th. 10 times that is like 10 times 10 clues. Might be like a quarter of the base, 100 clues, not even. But let's say it's a little bit odd. That's 10 to the 29th. 10 times that is like, let's say 10 times of those is like the base, right? Now we're to 10 to the 30th. We're going up kind of slowly here. We're already to the side of the base. What's 10 times the size of the base? Right? That's 10 to the 31. Right? 10 to the 31. Right? And 10 times the base. And then let's see, the city. The city's probably 10 times bigger than that. 10 to now. Look. 10 times, then that's like Djibouti, 10 to the 32nd particles. Right? We're only to the size of Djibouti, but 10 Djiboutis is now like, well, getting towards the size of Djibouti itself, maybe? Maybe not quite. 10 to the 32nd, maybe 10 to the 33rd. Now look, once you get size of like Djibouti itself, 10 Djiboutis is like 10 countries. Now they're small countries, they're pretty countries. 10 times that is like maybe the size of the Earth. But see how we're only to like 10 to the 35th? What's 10 to the 35th times all the stars in the universe? 10 to the 35th times 10 to the 22nd. 10 to the 57th? We're still not even there. We've got to go 10 times 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 10 all the way up to 85 and keep getting bigger by tens, right? That's why 10 to the 85 is a huge, huge, huge number, right? But it's nowhere, it's enough to all the particles in the universe. This number is so huge it's not even worth talking about. Like nothing is that big. I'm going to get this wrong. Do you know what this number is called? I think I'm going to get this wrong. I think it's this number. Close. It's called a googol. But that's not how you spell the Google we all know and love and search for crushes on, right? Right? It's called, this is the way Google was originally written down. It turns out some mathematician was talking to his kid about big numbers, and they ended up talking about, I think it was 10 to the 100th, right? And his kid named it and said, we're going to call that a Google. And he's like, oh, okay, cool, and he wrote it into a paper. And then somebody said, what's an even bigger number? Well, if you take a Google of these, a Google of Googles, right? That's going to be 10 to the 100 raised to 10 to the 100, right? Which is just an immense, immense number. And that's what's called a Googleplex, because they just wanted to make it another fancy name. Now, turns out, so Google, the website, was named after this number, although they spelled it differently. And their headquarters in Mountain View, California, you know what it's called? The Googleplex. Kind of, because it's like a multiplex. Kind of cool. Anyway, exponents, big, big numbers very quickly, and that's why we like them.
What happens when you start losing it?
When you start what?
What happens if you start losing it?
Like going smaller?
Yeah.
We get to other kinds of exponents. Good question. Very good question. Let's talk about that for a second. So we have some number, 3 squared. OK. And then if we go one more power bigger, that's 3 cubed and 3 to the 4th. If we get smaller, we get 3 to the what? Well, 3 squared, and then 3 to the 1. 3 squared is 3 times 3. 3 to the 1 is just 3. You've also got 3 to the 0. We define that as 1. It's another one of these ones where you think, why did they define anything to the 0 as 1? Well, so the rest of the math works out. Part of it is. Okay, but it also fits a very nice pattern, right? You can have negative exponents. 3 to the negative 1 is actually 1 over 3. Very good. Okay? 3 to the negative 2 is equal to 1 over 3 squared, which is equal to 1 over 9. Okay? Let's see why this. Let's see a different example. We actually talked about something like this yesterday. I know, I just lost you. We talked about something similar to this yesterday. 312.789. That's equal to 3 times 10 squared, because 3 times 10 squared is 100. Isn't that the 300 part? Plus 1 times 10 to the 1, because 1 times 10 gives you the tens part, plus 2 times 10 to the 0. This is where the pattern part of it comes in very nicely. 10 to the 0 we defined as what? 1. So 2 times 1 is just 2, which is the ones column. plus 7 times 10 to the, what's the pattern here? -1, right? 7 times 10 to the -1, which equals 7 times 1/10, or 7/10. Isn't that the 7/10 place? Yeah, OK. Plus 8 times 10 to the -2, which equals 8 times 1 over 10 squared, which is 8 times 1 over, what's 10 squared? 100, which is 8/100ths, because that's the 100ths place. And one more, plus 9 times 10 to the -3, which is 9 times 1 over 1,000, because 10 to the 3 is 1,000, which means it's 9 1,000ths, which is the 1,000ths place. So you see how 2, 1, 0, -1, -2, -3, it makes sense. The 10 part is right here. OK, it's the 1 divide. It's the 10 to the -3 is 10, or 1 over 10 to the 3. OK? All right. We'll get to a little more about that in a second. OK, let's see. We already did the product rule. Let's just do the rules, then I'm gonna let you go. Let me write this right up here. All right. We did the product rule already for exponents. The product rule was easy. Product rule says that we do it this way. B to the m times b to the n equals b raised to the m plus n. That's our product rule for exponents. We do have a quotient rule, which means a division rule. Can't spell. I-E-N-T. The quotient rule says this. B to the m divided by b to the n is the same as saying b to the m minus n. Let's see if this makes sense in a different form. We said that 1 over b to the n, remember what that equals in terms of negative exponents? 10 equals 1, well, let's do 100. 100 equals 1 over 10 squared. Sorry, 1/100th is 1 over 10 squared. OK? So, and that equals 10 to the -2. So in this case, b to the what equals 1 over b to the n? Negative n. So wouldn't that be like saying b to the m times b to the -n? Isn't that exactly the same thing? See how that's negative n is 1 over that, and that's 1 over that? I'm losing some people. It's all right. Don't stress too much. We're going to go over this more. Let's just leave it at the quotient rule says b to the m divided by b to the n equals b to the m minus n. OK? All right, there is one more rule. This is called the power rule. The power rule says b raised to the m power raised to the n power equals b to the m times n. OK? So an example of that would be like 2 raised to the 5th power raised to the 7th power. This is that Googleplex thing we were talking about where Google raised to the Google. Right? 2 to the 5th to the 7th is equal to 2 to the 35th because you just multiply them together. Okay? Those numbers get really big really fast too. You can see right there. Okay? All right. Tell you what, that was 50 minutes of like straight on. So let's take a break and come back at, let's say 5 after. All right. All right, so let's try a few of these. Try a few of these questions right here. I will give you this one because I kind of lied to you. I said any number raised to the 0 power is equal to 1, not 0. This is actually equal to the null set, or it just doesn't exist. It's like dividing by 0. Can't do it. 0 to the 0, undefined. OK? So don't worry about that one. Try the rest of these, and then try these ones over here too. I should have written it like this. If you don't like this one, let me write it like this. Let's see. 3 times 3 times 3 times 3 times 3 divided by 3 times 3 times 3 times 3. That 3 cancels, that 3 cancels, that 3 cancels, that 3 cancels. Left with 1 3. The 3 one? Remember the rule. The division rule is a to the m divided by a to the n equals a to the m minus n. What's 5 minus 4? 1. 3 to the 1 is just 3. Okay. Why did the French make such a loud aircraft? I want to know. I think that was Mirage. Wasn't that a Mirage? Air Force people should know this. All right. Any questions on these ones? Let's go through them real quick. 3 to the 20th. A power raised to a power, you multiply. Power times a power, if it's the same base. What if I had said 3 to the 4 times 5 to the 6th? You just leave it like that. Can't do anything else. Later on, when we get to some algebra, you'll see things like, well, you probably won't see too many things, but you might see something like x squared times y squared. You can't do anything with that, right? You can't, because it's a different base. It's like 3 and 5 are the x and y in this case. Okay? If you saw x to the 8th times x to the 7th, then you can add them, x to the 15th, right? But we won't do too much of that. Okay. All right, let's see. We talked about this one. 5 minus 4 is 1. 3 raised to the 1 power equals 3. 5 to the 0 is equal to 1. I told you that 0 to the 0, we're just calling undefined. 7 to the negative 2 is equal to 1 divided by 7 squared. And we know what 7 squared is, 49, so we can write it 1 over 49. 6 to the negative 1 is just 1 over 6. 10 to the negative 5 is 1 divided by 10 to the 5. And I just wrote out 10 to the 5. Powers of 10 are easy. If it's 10 to the 5, you do 1, and then 1, 2, 3, 4, 5 zeros. Easy. And then we said we can't do that one. Questions on those? Yeah.
I got a question. What if, like, how you got this 3 to the 4 by times what?
5 to the 6th? Yeah.
What if it was like 3 to the, I don't know, negative something times 5 to the positive whatever? Then how would you go about doing that?
Good question. What does this one equal?
Negative 1 over 3 to the 7th.
1 over 3 to the 7th times 5 to the 6th. You could rewrite this as 5 to the 6th divided by 3 to the 7th. Because, let me write it up here. Because 1 over a times b equals just b over a. That's like saying, well, you can say b times 1 divided by a, which is the same as b divided by a. So it's the same thing down here. You're right. That's a good question. 3 to the negative 7 times 5 to the 6th is 1 over 3 to the 7th times 5 to the 6th, which is the same as saying 5 to the 6th times 1 over 3 to the 7th, or 5 to the 6th divided by 3 to the 7th. You still can't change anything else on that because there's a different base, but you can write it like that if you want to. Good question. Anything else? All right. OK. Let me erase this. A couple more things on exponents. So one of the reasons we learn about exponents is so that we can get into this next little topic, which is scientific notation. OK? So scientific notation is a way to write numbers so that you can write them much in a shorter way than you might if you tried to write out the entire number. Okay? So let me write it like this. Okay? A positive number is written in scientific notation scientific notation when it is expressed in the form a times 10 to the n, where a is a number greater than or equal to 1 and less than 10. We write that this way, by the way. We say 1 is less than or equal to a, which is less than 10. And n is an integer. Now, that's a lot of words. OK, here's what that means. Okay? What that means is we're going to take a number, and we're going to write it in some form that has some number times 10 to the n. But that number there has to be between 1 and 10. For instance, 1.2 times 10 to the 6th. 1.2 times 10 to the 6th. Okay? Is it expressed in some number times 10 to the 6th? Yeah, and by the way, we replace, you don't do it like this. You don't write 1.2 dot 10 to the 6th. You always actually put in the little x for times. It's just the way the form is written. Okay? And some of the questions on your homework ask you to put things in this equation, or in this formula, or in this form. There's a little x button, I think. If I'm not mistaken, there's no x button?
You just have to use the asterisk.
The asterisk works? OK. Does it put the little x in there for you?
I don't think so.
I'm not sure.
Now you dot.
I forget. There's a, it's a what?
It's the dot.
It's the dot.
It's
Oh.
not the A.
Oh, it puts the little dot for you?
Yes.
It's weird.
It is weird. Well, I'll take a look at it and see. If I'll write an email to everybody if I figure it out. And write me an email if you can't figure it out. Let's put it that way. So anyway, 10 to the 6th is the 10 to the n part, and the 1.2 has got to be between 1 and 10. So this 82.5 times 10 to the third is not scientific notation, because this part is not between 1 and 10. It's bigger than 10, right? 0.2 times 10 to the 6th is not scientific notation, because that's not between 1 and 10. We're going to go ahead and convert these a little bit in a couple minutes, but just know that's the form. Okay? All right. Would it help if I put my notes online for everybody? So you don't have to either copy them down, or you can go back and look if you forgot to write everything down. OK, I'll start doing that tonight. If I forget, somebody email me and remind me. I'll do that. So then you can see all the different notes that we do. OK? All right. So did everybody get this down so far? All right. Let me erase what we've got here, and I'll show some other examples. OK? Sometimes on your calculator, by the way, the calculator uses this uppercase E to denote times 10 to the. So like 8e6 is really 8 times 10 to the 6th. Like this part is what the E means. OK? You might see that on your calculator. In fact, why don't we try to do a couple of these on your calculator? Well, it's not really gonna work. Let's see. On this calculator, if we want to type 8 times 10 to the 6th, I would type 8, and then it's actually EE on this one. The EE on this calculator. On some of the other ones, it might not be there. You hit the second button, and then the little x to the negative 1, which is EE, and it should say 8, and then it just, of course, it just says E. And then if you type 6, and then if you hit equals, it will say 8, 1, 2, 3, 4, 5, 6. Because 8e to the 6th is 8 with times 10 with 6 zeros after it. Okay? Make sure you can actually do those numbers in your calculator. Okay. All right. Questions on that one? All right. So we can convert, your calculator does it for you in this case, from scientific notation to decimal notation. Okay? Let's say we want to go from 3.178 times 10 to the 7th. 3.178 times 10 to the 7th. Okay? Well, what you do is, what's nice about these is because we live in a decimal world, in other words, we use powers of 10 when writing out numbers. This is actually pretty easy to do. It just shifts the decimal one way or the other, depending on what this number is. Okay? Anybody have any idea why humans came up with 10s for their number system? 10 fingers, right? Could have been 20, I suppose, with your toes. Or 21 if you count your nose, or your ears, 23 or something. I don't know. But anyway, it's probably good that we use 10. So anyway, what you do with this is you just shift the decimal place to the right 10 places. So 3, 1, 7, 8, 0, 0, 0, 0, 0, 0, 0, 0, 0. I'm going to count those in a second. If I start here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that. That's what that number is in scientific notation, or in going from scientific notation to regular notation.
Wouldn't it only be 7?
Did I count 10? Sorry. How's that? 1, 2, 3, 4, 5, 6, 7. Yeah, sorry, I was thinking 10 to the 10th. Thank you, keeping me honest. All right, so anyway, that's going from scientific notation into regular notation. Now, we can also write, and by the way, is this proper scientific notation? Is this number between 1 and 10? Yeah, it is, and that's a 10 to the 7th. Okay? You can also do it going the other way, like if you have a negative exponent, which means you go in the opposite direction. 2.4937 times 10 to the negative 8th. Okay? You have to go 8 in the opposite direction, to the left, right? So if I start here, I would go 1. I'll write a bunch of zeros this way. I'll try to stop at 8 this time. 1, 2, 3, 4, 5, 6, 7. Ooh, good. 8. And you put the little dot there, right? 1, 2, 3, 4, 5, 6, 7, 8. Okay? And then this one goes away. So it's 0.0000024937. And then this part, whoops, this part goes away. Okay, that's your number in non-scientific notation. Now you see why we write numbers like this in scientific notation. Did I do it wrong? Sure. Oh, okay. All right. Sorry, I did it wrong last time. I gotta ask, I guess. Anyway, this is how we write that number in regular terms. And again, the reason we don't write numbers this small is because the reason we do write them in scientific notation is because look what they look like when they're not in scientific notation. Not fun to deal with, all those zeros on either end. Okay. The way I remember learning it, 2.6 times 10 cubed. Okay. Well, actually, I was going to say here. How about this? Well, we'll get to an example. I'll wait on that example in a second. Let's try to convert to scientific notation. Well, I guess I will get to it. 0.00325. Okay, now to convert that to scientific notation, you have to have the number part be between 1 and 10. So where am I going to put the decimal to make this between 1 and 10? Right there, right? Okay, so I'll rewrite it. 0.00325. I'm going to do it right there. Okay? And then the way I always learned this was if you're making the number bigger, because you start with a small number and you're making it bigger by putting the decimal place there, the exponent has to get smaller. Okay? This number is actually times 10 to the 0, isn't it? Because 10 to the 0 is 1, right? So what's going to happen is this number is going to get smaller by the number of times you jumped over to get to there. 1, 2, 3 times 10 to the negative 3. Oop, actually, I lied. Times 10 to the negative 1, 2. Yeah, it is negative 3. Yeah, because we started at 0, 10 to the negative 3. Okay, let's try another one. Let's try going the other way. 17,028,430. Convert to scientific notation. The decimal place is going to go where? Right there, because 1.7 is between 1 and 10. Right? So it's going to be 1.702843 times 10 to the, and now we're going to go 1, 2, 3, 4, 5, 6. I wrote it kind of spread out like that, but only go, don't worry about the commas in there. Just go numbers. So 6. 1, 2, 3, 4, 5, 6. This number got a lot smaller, so this has to be bigger by 6.
Would it be 7?
1, 2, 3, 4, 5. Did I jump the comma?
Yeah.
Oh my gosh, I did. I even told you not to, and I did it. How about 7? 1, 2, 3, 4, 5. No, wait a minute. You guys are killing me here. I'm going to try this again. Hold on. Here we go. 1, 2, 3, 4, 5, 6, 7. Yeah, you're right, 7. Okay. Not my strong point, maybe. Okay. Anyway, 1.70243.843 times 10 to the 7th. A lot of times we will round numbers like this because the extra digits here don't really matter that much in some cases. So sometimes you'll see numbers that are rounded. You might go 1.7 times 10 to the 7th because it's really almost equal to that. But we'll get into some specific examples when you do that in a little bit. OK, let's try another one, and I'll try to get it right this time. All right, let's see. How about 9,283,000 to scientific notation? I'm not even going to do the commas now. Obviously, I'm brain dead when I try to do that. All right, 9.283, because that's the number between 1 and 10. 1, 2, 3, 4, 5, 6. Did I get it right? OK, that's how we do that one. All right, let's try one more. 0.000113. 1.13 times 10 to the 1, 2, 3, 4, negative 4. All right. Okay. All right. OK, so we did that. Let's see. So as a word problem, maybe. Well, this isn't really a word problem. $787 billion was the 2009 economic stimulus package in the United States. $787 billion. $787 billion. OK? And 787, and we said a billion is 10 to the 9th. 1, 2, 3, 4, 5, 6, 7, 8, 9. OK? Or we could say, by the way, we could say 787 times 10 to the 9th. But is that in scientific notation?
No.
Not quite. What do we have to do?
7.8.
Yeah, in this case, we'd put a 7.87, 1, 2. So if this got smaller by 2, this has to get bigger by 2 times 10 to the 11th. 7.87 times 10 to the 11th is $787 billion. There's a lot of dollars from your taxes, except in Djibouti. Because there's no civilians in here, right? Because they're all in the military? Yeah. Right now, you aren't paying taxes on your income. If you're married, your spouse probably is. OK. All right. When we want to do computations with scientific notation, you have to be a little careful with this. If you've got numbers that are in scientific notation and you're multiplying them or dividing them or trying to add them or whatever, you have to keep a couple of things in mind. OK? Remember that multiplication is commutative. You can move the pieces around if you want. 3.21 times 10 to the 5th times 1.4 times 10 to the 6th. Okay? You can move these numbers around because they're all multiplied by each other, right? So you could say 3.21 times, I'll put it in parentheses to the times, 1.4 times 10 to the 5th times 10 to the 6th, right? That's just the commutative rule. I just moved the parts around and got them in a different place, right? Can you do 3.21 times 1.4? Sure you can, right? That's 4.494, as it turns out. Okay? And can you do 10 to the 5th times 10 to the 6th in fancy using the same base rule? Well, it's going to be times 10 to the 11th. Ah, that was pretty nice. Okay? That was an easy way of doing that. You could have written this out. 3, 2, 1, let's see. 0, 0, 0, 0, 0. I'll count. 1, 2, 3, 4, 5. I think, yeah. All right. Times, right? Times 1, 4, 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 6. All right. You wouldn't want to necessarily do that long division, would you? And sometimes your calculator won't even fit some of these values. Like it's already too big, so you want to do it. But doing it with the scientific notation makes it pretty easy. So let's try one. You can use your calculators if you want for this other one. Try this one. Okay. 7.32 times 10 to the 7th, I'll write it like this, times 3.15 times 10 to the negative 5th. Okay. You can do that all at once on your calculator if you want, and I'm happy for you to do that. Okay. Or you can do it piece by piece, the way we might do it in like longhand or something like that. If you did it on your calculator, actually this one's a pretty easy one to do on your calculator. You would do 7.32, that double E thing, 7, and then the times key, and then 3.15, the double E thing again, and then negative 5. The negative is that negative button, not minus. Like there's two different buttons on here. One is the negative button, like the minus button rather. One's the negative button, which is this little negative sign in parentheses. Is that what you did? Didn't do? Yeah. So you tried to do it in your calculator. That's OK. And then if you did this, you should come out with 2.3058. Well, actually, it won't be. It could be like this if your calculator was in the right format. But it might be equal to 2305.8 maybe? Yeah. Like that. That might come out if you do it on your calculator. Then you'd have to convert that to scientific notation, which would be back to this one. Notice what happened when we multiplied 7.32 times 3.15. We got a number bigger than 10. So we have to, once we did this, and then we did 7 minus 5, because 10 to the 7th times 10 to the negative 5 is 10 to the 10 squared. And then we had to convert this properly to scientific notation. Some of you guys might get this far on the quiz and forget to go to this one, and I'll take like 1 point off. That's one of the things I do. On tests, I will give you partial credit where it's deserved. So if you get halfway through a problem and you're like, I don't know how to do the rest or whatever, I'll give you the credit up to that point, right? Or if you did this and you got to this part, let's say you did this. Let's say you messed this multiplication up and you said it was like 21.326 or 7 or whatever. You just did it wrong. And then carried it on, and this answer ended up with this number instead of this one. I would still only take 1 point off, because you still did the rest of it right. You just messed up the one part. So I'll try to give you the most points that you actually deserved on the test. Okay? All right, questions on this one. Now you know how to use your calculator to do it too. All right, let's see, that's that one. Dividing. Dividing is uses this division exponent rule. Not any harder, you just have to remember the rule. So, for instance, 8.54 times 10 to the third divided by 2.5 times 10 to the fifth. By the way, those of you who might end up as engineers will see this a lot, especially when you're doing things like chemistry or physics or whatever. You'll have to do these sorts of things. You have to divide them, divide scientific notation. Again, you can do this on your calculator. This one you may have to be, this one's not too bad on your calculator. A lot of times when you're doing division, you're going to need parentheses around things. So it's always good to put them there on your calculator if you're going to do it. But you can do this two different ways. Well, one way really. You can do it on your calculator, or you can do it this way. 8.54 divided by 2.5. And then you're going to do times 10 to the third divided by 10 to the fifth. You kind of do these parts separately now. You do this out, right, and you get 3.416, sorry, 3.416, right? And then you do this. 3 minus 5 is negative 2 times 10 to the negative 2, like that. Okay? And then you did this part, and you did this part, and then you ended up with just the answer like that. Okay? Try this one. Yes, Amy.
What does that look like on the calculator?
On the calculator, good question. 8.54, the little double E symbol, 3, right? Divided by, you do the divided by, and then you do 2.5, the double E thing, 5. That should give you the right answer. It will give you an answer that looks like 0.003416. Nope, 0.0. Yeah, like that. 0 point. It'll give you that answer.
Syntax error.
Syntax error? Let me see. You might have put an act in.
No, that's, I mean, it come up like that. You know, you gotta do it.
8.54 EE3 divided by 2.5 EE5. It worked for me. Some of you guys have calculators. Do you have the double E button on there? Is the E, it's just the E button, or is it?
It's EXP.
E, oh, it's EXP. Okay. Hold on. No, it is EXP. EXP is the one that works.
No, not for those.
For yours, it is.
Well, yeah, it's an exponent, but you gotta actually raise it to the power.
No.
By 10.
No, you don't. You can do it that way, but the better one on this one is to use EXP.
Oh, mine isn't.
Try this. Try this. Just do it like this. 8.54 EXP 3 divided by 2.5 EXP 5. Hey, there you go. So yeah, you can do it the other way. If you do the other way, you have to use parentheses.
No, you know why?
Why?
I think I was pushing both buttons, and it pissed me off, so I went to one, and it worked, so I
Oh.
stuck with it.
Hey, whichever one you want.
To skin a cat.
Yeah, exactly. 2 ways to skin a cat. All right. Did you figure it out, Amy? OK, good. All right. So let's try this one. 6.15 times 10 to the negative 5 divided by 3.2 times 10 to the negative 7. Try that one on your own. Oops, let's make it 6.16. Doesn't actually matter. We'll do 6.15. We'll leave it at 6.15. Sorry, whatever. Do whatever you want. I just have a different. Do either one. I'll write both down. If you did 6.15, you're going to get 1.921875 times 10 to the 2. If you did 6 point, what did I say, 1, 2? You're going to get 1.9125 times 10 to the 2. No?
That's what 6.16.
He's got 9215.
Is it 9215?
It's 1.925.
Oh, you're right. 925, thank you.
He's still doing the. I'm sorry.
If you do 0.16, it's just going to be
1.925. Yeah.
Where are you getting it?
If you did it on your calculator, you're going to get 192.1875. But remember, I'm asking you for the answer in scientific notation. Because this is 192.1875 times 10 to the 0. You need to convert this properly into scientific notation, meaning this is going to go over by 2, 1.92 times 10 to the 2. Okay? Iglesias, you got this one? Okay. Sharifa, you got this one? Good? Good?
I got a question.
Question, Dwan.
The answer that I get the answer that you got.
Yes.
And I don't have times 10 to the.
Are you doing it in your calculator? Okay. You're going to get this one, right? 192 or 192, 1875 or 1925 times whatever, right? That's because your calculator doesn't report it in scientific notation. If it can fit it in, it won't put it in scientific notation. So you do have to convert it yourself. There's actually a way to put your calculator in scientific notation so that it reports the answer in that, but I would suggest against doing that because then you'll forget to move it back, or you won't, but you can if you really want to. But anyway, yeah, you're getting the right answer. But if I asked it, if you gave me this answer, 192.1875, sorry, 192.1875, I would take a point off because you got the right answer, but you didn't put it in scientific notation. If I asked you.
The calculator gives me 1.92. So.
And then did you do? But there's no e. Oh, so
1.921875.
you may have done the exponents slightly wrong or something like that. Or didn't put them in at all. Did you put the exponents in at all? All right. Tell you what. When we do our next break, just see me. We'll do the right buttons. Okay. All right. So that's basics of scientific notation. Let's see. Rounding. Sometimes you will be asked to round. If you have two numbers, like, for instance, 6.15, let's see, times 10 to the 12th divided by 3.2 times 10 to the 5th. Okay. How many digits are in this piece right here? 1, 2, 3. And how many digits are in this piece? 2. Okay. Turns out if you're doing scientific numbers, like you're using numbers that are have only a certain number of digits after there, your answer should have the number of the least amount in it, and you should round. I'm not going to care that much that you do it, but it's important to know about this concept. It's called significant digits. Okay, and you guys probably know by now I'm kind of a nerd, right? My favorite joke. Here's my favorite joke. Two guys walk into a natural history museum, with dinosaur bones and everything. And one guy says to the other guy, he says, "What's so funny? I didn't hit the punchline yet." One guy says to the other guy, he says, "See that dinosaur over there? That dinosaur is 1,000,004 years old." And the other guy says, "How do you know that dinosaur is 1,000,004 years old?" And the first guy says, "Well, because I came in here 4 years ago and they told me it was 1,000,000 years old." Right? Well, maybe it's not that funny. It's my favorite joke. Make sure you laugh. No, so the point is that that dinosaur will be 1,000,000 years old today. It'll be 1,000,000 years old a year from now. It'll be 1,000,000 years old 100 years from now. It'll be 1,000,000 years old 100,000 years from now. Because you can't get any better than that. Like, they only know within a certain range. And that range tells you that there's really only one significant digit there. 1, 2, 3, 4, 5, 6. OK, I know I said that. Well, if you did this in scientific notation, that would be what? 1 times 10 to the 6th? How many digits are there? 1. You've only got one significant digit, one digit that matters. So you can't say that the dinosaur is 1,004 years old just because you were there 4 years ago. Right? It just doesn't make sense. The next time that dinosaur has any kind of a birthday, as far as it knows, it'll be 2,000,000 years old. Right? Because that's the best you can do as far as calculating how old it is. That becomes important when you do things like dividing scientific notation. Because if you were to divide these two numbers, is this the one we just did? This is the one we just did. Right? You end up with 1.921875, right, times 10 to the different exponent, times 10 to the 7th. But notice all these extra digits, they don't actually matter. This is like saying that 4 years for the dinosaur thing. Those ones don't actually matter. The only ones that matter are the 2 that come from the smallest one here. So really, you should round this to 1.9 times 10 to the 7th, and all these ones don't actually matter. Okay, it's just a little scientific thing. If you're taking science classes later, you'll have to know that those ones don't actually matter. Yes, they matter on your calculator, but they don't matter because maybe we rounded this one to begin with, 3.2 times 10 to the 5th. Maybe that's like the dinosaur that's 1,000,000 years old. It could actually have been born 1,004 years ago, but you're not going to know. Right? So you got to just keep the numbers as small as you want. I will never take off points if you give me all those digits. Just think about that so that next, if you ever take a science class or whatever, you'll know. Okay? What are you guys majoring in anyway? Anybody majoring in kind of science or engineering or want to? I know, Andrew, you said that. What are you majoring in, Andrew?
Well, I'm majoring. Well, right now I'm taking this for finance, but I want to go for nautical engineering.
Nautical engineering. That's cool. Oh, aeronautical. That's cool. Awesome. Awesome. OK. How about you?
Trying to get into mine and mineral engineering.
Mine and mineral engineering. OK, good. You guys are going to have to pay attention in here. You engineers. Anybody else? You said civil, maybe. Anybody else? How about any business majors? A couple business majors in here. Good. Finance. How about, let's see, English, social studies, history, anything like that? No? Yes? What do you just want to? Sociology. There you go. Let's see. What have I missed? Business, science, general studies. General studies. OK. All right. All right. That's good. Anybody else? Did I miss anybody else's? No? OK. Lots of different majors out there. You got time. If you're like a freshman or whatever, you still got time to decide these things. Still got time to decide these things. OK. Let's do this. We've got one more kind of medium-sized section. Let's just take another break right now. Come back in 10 minutes. Come back at 5 of 8. OK, here's what we're going to do. We're going to talk about problem solving for a few minutes. We're going to do some problem solving. Later on in the class, we're going to learn how to solve some of these problems actually using algebra, which I think is sometimes easier. Some of the problems you really can't do algebra very easily on them. And so we'll try that. But the key to solving problems, especially word problems, right? The first big step, and you can read a bunch of these things on page 26 of your textbook if you want. Page 26, there's a whole list. I'll kind of write some of these things down. We'll talk about them. How do you actually solve problems? Well, number one, understand the problem. Understand the problem. This is harder than it sounds sometimes, because you have to be able to read the problem. You have to be able to understand all the words, obviously. You have to be able to process what's being asked. And that's sometimes the hardest part. You forget what's being asked. And then you go down this big, long path, and you realize, I don't know what I'm doing here. You don't even remember what was the question, right? So that's the big thing. Once you understand the problem, once you figure it out, you made it. Only a minute. That's not bad. Not bad. All right. Once you understand the problem, then you have to do this. You have to devise a plan. Devise a plan. There, should have asked him to grab something for you at the next. Devise a plan. There's lots of different ways to do these plans, OK? Let's just write down a couple. You could recognize some pattern. Recognize a pattern. Remember the first thing we did last night where we looked at the recipe and we walked through, hey, how do you double a recipe? Oh, you do, it's 2 times as much. And how do you get the 2? Well, it's twice as much of what you want, and then you multiply that by the original cup. You're recognizing a pattern there when you're figuring that out. Okay? Another good thing, draw a picture. Sometimes, if you can draw a picture about the problem, it makes solving it much easier. In fact, if you draw a picture and it's got enough parts to it, you might be able to just count to figure out the answer. Okay? You could make a table. A lot of times we'll make tables for things when we have a whole bunch of data and we want to organize it. And then once you organize it, you can do whatever calculations you need from the table, or a list, in a table or a list. Okay, you list out what you're looking for. We'll do some examples of that in a minute. Sometimes it helps if you work backwards. So you kind of know what the answer is going to be, but how do you get there? Like you might have an idea of what the answer might be, but if you kind of start towards the end of the problem and work your way forward, that's not a bad problem solving technology or technique. You can also solve an easier problem. That's another one where the recipe one came into play. When we tried to double that recipe, when we said, 2 1/4 cups of water, and we wanted to go from 3 to, I don't know, whatever it was, 7, made 3 brownies to 7 brownies or whatever, and you needed 2 1/4 cups for 3. How did you get to 7? Well, the easier problem was just go from 3 to 6, because you're doubling it. And now you know twice 2 1/4 cups. Oh, how did I get 2? 6 divided by 3. Ah, well, there's your pattern. 6 divided by 3. Well, you're really going to, in this case, do 7 divided by 3 times the 2 1/4, and that's how we solved it. Okay, we solved an easier problem to get to the harder problem. Okay, and for those of you who weren't here yesterday, you have no idea what I'm talking about, but we worked on a problem like this yesterday. What's that? Potatoes, that's what it was. Yeah, that's right. Orders of potatoes or whatever. Flake potatoes, yeah, exactly. OK, so we could solve an easier problem. Another way to do it sometimes, trial and error. I know that sounds terrible sometimes. It's not that bad. Sometimes you have to do that. When we get to this thing where we call factoring, right? When we get to this thing called factoring where we want to take a, well, actually, we want to take something like x squared plus 2x plus 3, and we want to turn it into its component factors. We'll get to what that means in a few weeks. We have to do a little bit of trial and error to solve that. So it's not a bad mathematical technique. OK? X and x. X plus 2, x minus, no, sorry. X plus 3 and x minus 1, maybe? I think. No, that doesn't work either. You can't do this one. You can't factor this one easily. It would have to be -3, make it easier. But anyway, trial and error is one of the ways you can do these things. Okay? You could, let's see, we've got lots of different problem solving strategies. We could relate the problem to an earlier problem or a previously solved problem. A previously solved problem. In some sense, that's what we were doing with the cups of water for the mashed potatoes as well, right? We solved some easier problem. Okay? Look for the catch if it seems too easy. In other words, if you can go, I know the answer to that, and you're like, that was pretty easy for a 10-point problem on an exam, right? Well, maybe there's a little more to it. You can't just go, oh, I know the answer. Sometimes you have to look for, oh, he's asking for something else or something else. Okay? The last one, use common sense. A lot of times, you have to just think, OK, what am I trying to do? I mean, if I had asked you, so yesterday when we talked about this mashed potatoes problem again, you guys probably could have used some common sense to figure that out. It might have taken a little while. But you could have used common sense if you'd said, OK, how do you actually get from certain amount of, how do you make a recipe bigger? Well, you have to start using some common sense to do that. OK? Once you do that, step 3, those are all planned. And by the way, you probably have more ideas of your own. OK? Solve the problem. Solve the problem with your plan. Like you got a plan, you pick one and you go, OK, I'm going to make a table and go for it. Well, then solve it that way. OK? And then finally, if you can, check your answer. And I mention this, I'll probably mention this every day of this class. If you have a problem where you can check the answer, do it. It takes like 1 minute to check the answer. And if you got it right, you can just move on and know for certain you got it right. If it's wrong, you got to go redo it, right? And so you might as well. If you can check it, check it. OK. Lots of different problem-solving strategies. This is the way normal humans like us solve these problems. The super brilliant scientists, there was a guy named Richard Feynman, who was a really famous physicist in the 20th century. He said his problem-solving technique was read the problem, think very hard, write down the answer. That was his problem-solving strategy, right? Doesn't quite work like this. OK? All right. Let's do an example of this. OK? Any questions on the problem-solving method? I know it's all words and whatever, but write these down. Just kind of think about these. Don't memorize this list, but think about some of the ways that we use these ideas in the problem. OK. Anybody grow up on a farm? Anybody grow up on a farm? No? Not many people do these days. Farms anymore. Let's say, we'll do a farming problem, a really important one, on chickens and pigs. Chickens and pigs. All right, here's the problem. Really important problem. Farmer Smith has a farm, chickens and pigs. OK? The Farmer Smith, has 20 animals. OK? And those animals have 64 feet. How many chickens does he have? And how many pigs does he have? How many chickens? And then pigs. Okay? We will eventually figure out how to do this problem using some algebra. Let's not worry about that right now. Let's just use a couple different problem-solving techniques. Okay? One of the problem-solving techniques was trial and error. And you guys all grumbled about that. Let's guess that there's 7 chickens. Why not? Right? Let's just guess. 7 chickens. If he had 7 chickens and the rest were pigs, how many feet are there total? And don't worry about his feet. Just the pigs and the chickens' feet. OK? How many chickens and how many pigs? If he has 7 chickens, so let's say he has 7 chickens, how many feet per chicken? 2. That gives you how many feet total? 14. OK? If he has 7 chickens and there are 20 total animals, how many pigs does he have? How about 13? Because 7 chickens plus 13 chickens gives him, or 13 pigs gives him a total of 20 animals. What's that? Well, I don't know. Let's find out. 13 times how many feet do pigs have? 4. 13 times 4 is 2, 1, 52. For a total feet count of 66 feet. No. We said he had 64 feet. So we guessed wrong. But who cares? We're not done with the problem yet. If, it was a pretty close guess. If we have 14, or if we said we had 7 chickens and we have too many feet, does that mean we guessed too many chickens or too many pigs? Too many pigs. So what's our next guess going to be? 8 chickens. Let's try that. 8 chickens times 2 feet gives you 16 feet. So now we have how many pigs left over? 12, because there's got to be 20 total. 12 times 4 is 48 for a total of 64 feet. Done. Okay, that's one way to solve this problem. So he has 8 chickens. 8 chickens and 12 pigs. Okay, do you see how that problem solving worked? We just guessed and then went with it and ran with it. Okay? We could have drawn a picture. Okay? A picture of chickens and pigs. Right? Maybe it's a long way. All right? Let's do it this way. Let's just really quickly sketch out 20 chickens. 1, 2, 3, 4, 5. We're just going to do them from like the back, but forget about the rest of the chicken, right? We just need that, and we need feet in a minute, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. There's our chickens, okay? And let's draw all the feet. 1, 2, 3, 4, 5, 6, da 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 da, all the feet. This is called Sketching 101. Okay? We drew all the feet. And how many are there? Okay? There's now 40 feet. But we need how many more feet? 24 more feet. 1, 2, there's a pig. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Those are now pigs. How many chickens are there? 1, 2, 3, 4, 5, 6, 7, 8. 8 chickens. The rest, how many did we say? 12. 12 pigs. That wasn't that hard, right? It's pretty easy to do once you if you thought of it that way. You drew a picture and you did it. Uh-oh. What's wrong? You wouldn't have thought of that necessarily. Okay, all the ones with 2 feet are chickens. Right?
You just had 40.
Ah, we did, but then we turned them into pigs. All right, it's magic. We started with 20 chickens with 40 feet total, right? But then they were all chickens to begin with. But then we said, no, we can't have that many chickens. We need more pigs because we don't have enough feet. In fact, we need 24 more feet. I just started adding feet. When I added 2 more feet, that became a pig.
Oh.
And now that's a pig, and they're all pigs until I ran out of feet to add, which was 24 feet. Right? It works, right? Okay, it works. All right, so these are just examples. And if you didn't think about this method, fine. You can think of some other method. That's kind of a clever one, really, right? That one's kind of a cool one. Okay.
So how would you check it?
How would you check it? You would say, OK, I've got 8 chickens and 12 pigs. 8 chickens and 12 pigs. 8 chickens times 2 feet gives me 16 feet. And then 12 pigs times 4 feet gives me 48 feet. And then if I add those together, I get a total of 64 feet. There's your check. Because you said, OK, look, I've got 64 total feet, and I've got 20 total animals. That's how you check it. Okay? All right. OK. That's another way to do it. A third way to do it, let's make a table. Okay? A table. Let's say that you started out the table. This is kind of like the guess and check method, but let's just start in the middle somewhere. 5, 6, 7. You could do this for as many. You could write down all the number of chickens. This is the number of chickens, and then we're going to have the number of pigs, right? And let's do a table here. Okay? And let's say, so chickens and pigs, and then let's say, oh, actually, no. We'll do chickens. We'll do chicken feet. Anybody getting hungry? Chicken feet, and then pigs, and then pig feet, and then, let's see, and then total feet. Okay? Chicken, chicken feet, pigs, pigs feet, and total feet. Okay, 5 chickens, how many feet do you have? 10. That means if you have 5 chickens, you have how many pigs? 15. Let's just do this. 6 chickens means you have how many pigs? 14. 7 chickens mean you have 13. 8 chickens, 12, right? Okay. 12, 14, 16. 15 times 4 is 60. 14 times 4 is 54. 6. 13 times 4 is 52. And 12 times 4 is 48. And you add the total feet, chicken feet plus pig's feet, 70. Let's see, 8, 68. 52 and 14 is 60, 56. And then 66. 66, and then 64. Okay, and then you go, oh, look, now I've got it, 20 animals and 64 feet. So 64 feet, and we know the total was 20 animals. You can do it that way, or you could, once you get this method going, you can go, look, every time I turn a chicken into a pig, I gain 2 more feet, right? Or I guess every time I turn a pig into a chicken, I lose 2 feet. And you could go down that way, do it that way. So this is the table method. Okay. All right. Any other ways you can think of to solve that? There is an algebra way too, which we'll get to later. Okay. All right. Let's see. I don't want to do that problem. Let's do this problem. Anybody ever work retail? Work in a store where you're selling clothes or something else? Ever have to make change for someone? Right? Yeah, a lot of times you just type it in the computer and it tells you. Or you scan all the items, push a button, and it tells you how much change. Sometimes you actually have to make the change for somebody, and you have to count it out. How do you make 35? We're done with chickens and pigs. We will revisit this during algebra. Come back and you go, oh no, not chickens and pigs again. Okay. How do you make 35 cents change? How do you make 35, whoops, 8, 30. What am I doing? I keep writing an 8. It should be a dollar sign. I'm listening to the plane. Dollar sign, 0.35 change, or 35 cents. That's 35 cents change. How do you make 35 cents change? You can't use pennies. No pennies. Okay? Now, there's a lot of different ways. We're going to do a table, right? There's no coins big. You can't use a coin bigger than a quarter, because that doesn't. There aren't any that. Like the next one's a 50-cent piece, right? But you can do that. So let's see how we might do this. Let's do a table: quarters, dimes, nickels. Okay? And try to do these tables, if you can, in some sort of order that makes sense. 35 cents. Let's start out with how many quarters? 1 quarter, let's say. Okay. If we had 1 quarter and how many dimes, let's say? 1 dime, that's 25 cents plus 10 cents is 35 cents. How many nickels? 0. Okay. So we're done with 1 possibility. Okay. Are there any more possibilities with a quarter? Okay. No? Some people are saying no. There are. Let's say you had 1 quarter and 0 dimes. How many nickels do you have to have? 2. Okay. Any more choices with quarters? No. How about 0 quarters? Okay. Well, what's the most number of dimes that you need to go into 35 cents? 3, which leaves how many nickels? 1. Okay. 0. How about only 2? Then what would you need? 20 cents. You need 15 more cents, or 3 nickels. Any more? 1. 5 nickels now, because you got 10 cents plus 25 cents. And then finally, if you have no quarters or no dimes, how many nickels do you need? 7. Now, we figured out all the combinations. Except for pennies. If I'd said pennies, you'd be here all day, right? Be lots more combinations. Okay? And how many different ways are there to make change? 1, 2, 3, 4, 5, 6. Okay, makes sense? Literally? No pun intended. Okay? And you'd want to make sure and add these up correctly too. So that's the way to do this. Okay? All right, let's do another example. Let's see, Professor Dumbledore. In other words, Harry Potter, right? Has 3 robes and 2 wizard hats. All right? Professor, let's see, I'll erase this. He doesn't care about making change. OK, Dumbledore. Someday I want to write a book where some dude in Djibouti is using it for math class. I think that'd be kind of, means you've made it, right? All right, Professor Dumbledore has 3 robes and 2 wizard hats. Okay. How many outfits can he put together? How many outfits? And by the way, we'll get to this problem later in when we do probability, a little bit later in the year, in the semester. Okay? What are we looking for? We're looking for the number of outfits, which is a number, right? We're just looking for a number. Okay? And in this case, let's do a little diagram. Okay? Here's the diagram I'm going to do. He's got 3 robes. Very good. He's got 3 robes. Robe 1. Robe 2, and robe 3. If he's wearing robe 1, how many choices does he have for hats? 2. I'll do H1 and H2. How about robe 2? H1 and H2. And the same thing for 3, H1 and H2. Any other choices? He's got a robe and some hat on, and those are his choices. 1, 2, 3, 4, 5, 6. Done. Okay, 6 different outfits. If he has 6 outfits, did we answer the question? How many outfits? Yes. We did. Okay, and we can check it. All right. So those are some various problem-solving strategies. Here is what I want to do. Yesterday I gave you we're done with the learning part tonight. Now it's the practicing part. Okay? All right, so you can shake it out if you want. Here's what I want to do. I've got, I don't know why, because we scrunch things up and because there's a couple things in here, I've got 4 more things. I should have stapled them all together. 2 of them are problems that you can solve. 3 of them are problems that are like problem sets. The 4th one is the practice exam. Okay, so here's what I'm going to do. I'm just going to start handing these around. Grab 1 of each. Yeah, you can do in whatever order you want. By the end of handing around, you should have 4 more things, and then 2 from yesterday. All right. And what we'll do is at least until 9. Well, yeah, at least until 10 of 9 if you're really sick of this stuff. I want you to work on these things, okay, in any order you want, and then just yell at me, and I'll do whatever problem you're stuck on the board. Okay. Did you get that one already? This is your 4th one. Okay.